Okay. So the next thing that I want to talk about, is this idea of having this distribution around the sample average, right? I'm going to drive home some of kind of the topics that we brought home from our last demo. Okay, so what are some of the things that we want to kind of study and look at? So we talked about this idea of center, this mean, and this idea of variability. And so how far is the data from the center, from the mean? And can we quantify that? Can we be more precise with that? And, you know, why is it the fact that because of the central limit theory, why these distributions that we generate, why do they come out bell-shaped? Okay. And so these are kind of, you know, the first two questions are kind of, you know, theoretical, but they are. And then, but in the practical terms, so the one that I really kind of focus on, like, because I'm a computer scientist, right? I'm not a statistician, so I like to just know how do I get my job done, and hopefully what we can do today is kind of demystify some of the magic, right? Some of this stuff kind of seems like magic. And so the question I really want to focus on today is how is the sample size related to the accuracy of the estimate? Because at the end of the day, that's the thing that we want to know, right? We want to know, right? And we see this all the time, right? You know, in presidential polls, they say, you know, 54%, you know, blah, 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 right? And they always say plus or minus, right? That's, you know, some measure of the accuracy of the estimate. And so the question over the next couple lectures, I hope to kind of, you know, show you how we get that plus or minus. Like, how do we get that for a given sample size? How is that related to the accuracy of the estimate that we're getting, right? Those are the questions. And it is my hope kind of, you know, in the next few lectures and in this course, we take away some of the magic from that, or it doesn't seem so magical from there. So, all right. So we've seen from the central limit theorem, we saw that regardless of the distribution, if we do random sampling, provided that the sampling is indeed random and our sample is large enough, we're gonna get a bell-shaped distribution, an empirical distribution of the sample from that. Okay, and so why is this a big deal? And this is a big deal, by the way. And why is this a big deal? Is because these sample averages that we get, right? And if we can say something about those sample averages, we can say something concrete about the distribution and the accuracy, right? They act as a proxy for our population. These sample averages are going to be an estimate of the population average. Because remember the name of the game is that we don't have the resources in most cases to sample the entire population, or to survey the entire population, right? To get everyone. So we're going to take a sample and we want to know how close would this average be to the actual population. And we're going to kind of give you the tools to kind of help quantify that. So first, I want to talk about, you know, why is there distribution? Okay. So we have, right, we're going to take this sample, we're going to take this random sample. And once we have that data, once we have that sample, there's only one average. It is literally the sum of our data divided by the length, all the elements in there, right? That is it. That is it. And so if we just have that data, why are we showing you all of these like histograms? Well, because we're sampling the population, and the sample could have come out very different depending on who we sample, right? And so because who we sampled is important to kind of how that sample comes out. A different sample might have come out differently. Okay, and so what we mean by that is that when we take a sample average, from a population, that is only one of many possible sample averages that we can take, right? And there's just many of them. So if we actually wanted a complete kind of distribution, right, we can imagine taking all possible random samples, the same size as the one we picked, like 100, 200, 10, 900, right? There's tons of them. Imagine if you had a population of 10,000, how many different ways are there to take a sample of 100? There's a lot. Each of those samples, every possible kind of combination of samples has an average associated with it. And so we can think about this distribution of sample average as the distribution of the averages of all possible samples. So what does that look like? Okay. And so here we have our population, right, on the left, all the way on the left side. This is, after a while, you get kind of good at actually knowing the population just from its distribution, right? This is our traffic delay data, right? And so that is the actual population. And we can take many possible samples of that, of a particular, right? In this case, 400. And so imagine if we took all possible combinations of sampling 400 and put them all together, right? So notice each particular sample of 400 from there, right? It's a rough approximation. It's a rough approximation of the population, and we can get a sample. We can get the sample mean from each one of those, and that just becomes 1 point in our histogram. Okay, from there, and so you can see that we're going to get this distribution from there. Okay, so if we have a large random sample, we've seen that distribution, the distribution of the average, is going to be roughly bell-shaped. So the one question that we want to kind of ask ourselves is, where is the center of that bell curve, and how wide is that bell curve, right? Because we know that regardless of the distribution of the population, if we conduct random sampling, we're going to get a distribution centered around the mean, and the variance is going to be proportional. It's going to be kind of the variation is going to be centered around the standard deviation, is going to be centered around the mean from there. Okay, so the center of the distribution is just going to be the average. Okay, so the distribution of our sample average is going to be centered around the population average. Now that's kind of the, the way I think of it, that's kind of just not terribly controversial, right? That's a pretty kind of straightforward result there. And so, but now the variability of the sample average, right? So we're looking at the histogram, the distribution of our trials. Why is this important? Well, just like the center, the spread is going to help us. It's going to help us identify which normal curve is the distribution of the sample average, right? So the center gets to the heart of the population average, and the variability, right? So the center is going to give us the number. That's going to be our estimate. So the center of our sampling distribution is going to give us the number. That is going to be our estimate. Where variability comes into play, that is going to give us an indication of how accurate, how confident we are in that sample that we came up with, that sample average, is an estimate of the population. Okay, so the two of them kind of work together. The mean, the center, gives us the actual number. That is going to be, you know, we're going to say that is the average height, or the estimated height from our that we think the population has. The variability of this distribution that we get is going to allow us to say how confident we are, how confident, how accurate that estimate is. And what's nice about this is that as we saw, kind of there's this relationship to the sample size and the accuracy, the sample size and how much variance we get in the distribution. And as we saw, as the sample size increases, the variance, the standard deviation around the median, decreases. So another way of saying that is that the larger the sample size, it helps us get a more accurate measure. And so how do all of these things come into play? Let's take a look. Okay, let's go back to our flight data again. And again, we're using that because we have the entire population. So we can really see, we can see how our estimates do compared to the actual data. And so this is everything that we've done before. Our population delay, our population standard deviation, and our percentile from there. Okay, these are the exact same functions. I didn't try to kind of pull a fast one on us. We're just taking one mean, and this is our function to do 10,000 of those trials for a given sample size, right? And again, this is how many people, how many surveys are we doing? How much are we plucking from the original? And by the way, you know, so how many? What was our, yeah? So never mind. Okay. And so now what I want to do here is, okay, so what we're doing here is kind of putting it all together. This is just a little helper function that's going to select from our sample, generate our statistics, and just plot everything out in one little function for us, okay? Because we're going to run this with some various sample size. We're going to run this with like 100, 400, and 900 from there, okay? And so there's nothing, this is very similar to the previous demo that we did. We just put fancy titles on there. And then, but I want to draw you to this part here. So we're spitting out a little bit of some of the statistics here. Okay, so our sample size, and this is all comes directly from this function here. So our sample size was what we passed in, right? So that's how many samples we took. Population mean, that's not gonna change because that is the actual ground truth. And you can see that the sample means, it actually, even with 100 from this particular sample, remember, every time we run this, we're going to get slightly different answers for the average of the sample. But you know, even with 100 samples, in this trial, it did quite good. But it's again, it's going to vary every time we run that. And so, because we actually have the data, we have the standard deviation of the population. This is ground truth, okay? And because now that we have a histogram of our simulation, we can also look at the standard deviation of the sample means that we came out with, okay? And so, again, we're going to be subject kind of roughly, so we know this graph, because we haven't normalized this, so we didn't put it in standard units. And so we know that the sample, the average is going to be around 16.6, so somewhere around here. And then the sample mean, right? So one standard deviation is going to be plus or minus, you know, 3.9 of 4, okay? But one thing that's kind of interesting to take a look at is this ratio, okay? Of this ratio of the population standard deviation. So this, again, this is the actual distribution, how much the actual data varies, the population data. And And normally we don't have this, and compare it to the standard deviation of our sample, okay? And we can actually take a ratio of that. And so if we take a look at that, that's 3.9. So every time it runs, I get different numbers, right? So if we do that over here, so we get this notion, we get this number that's pretty much 10, okay? And so what is this number saying? So this what this is saying is roughly the standard deviation of our output of our simulation is about 1/10 the standard deviation of the population, right? So this is the population divided by R. So if you take the reciprocal of that, the standard deviation of our results, right? And this, again, this is this idea of how accurate our estimate is about 1/10 the variance, 1/10 the standard deviation, 1/10 the 1/10 the standard deviation of the population, okay? And so let's just run that again. I'm just going to run all of these. They take a little bit of time to run. And let's look at kind of how, and we know when we run with a larger sample size, the standard deviation of our output is going to be smaller. And we see that, right? The standard deviation of a sample size of 400, what was it before? It was 3.9. And now it's down to like 1.933. All right, so what does that look like? 1.933. And again, looking at the ratio from that, so this standard deviation, and again, this is the standard deviation of our simulation is an estimate of how accurate our result is. It is before we had this ratio of 10, like so 10%. Or sorry, 1/10, 1/10 of the population standard deviation. Now it went down to 1/20th, okay? It went down to 1/20th from there. And so now what we're saying is the standard deviation that we got was 1/20th of the population standard deviation. And kind of following this out, if we run with 900, we get 1.27. And again, you see we get very close to the standard deviation is going down. And it is now 1/30th of the population's standard deviation, okay? And so we kind of see here that, as we saw kind of from the last demo, that as our population increases, our sample size, as our sample size increases, we're honing in, we're narrowing the standard deviation, the variance of our estimate. The bounds, right? The plus or minus bounds are getting smaller and smaller. But now we see by looking at these ratios, the standard deviation of the general population comes into play from that, because these ratios, right? These numbers of 10, 20, and 30, they're not arbitrary, as we're going to see in a second. Any questions? All right, I will take no news as good news. And so let's see this. Okay, so all right, let's have a couple of distributions. This one I won't send you into a breakout room for, but let's take a moment to think about this. Okay, all right. So what we've shown here is, so this is kind of from our demo from last time. So the gold histogram shows the distribution of blank values, each of which is blank. Okay, and so the first blank. Well, yeah. I'm going to pause the recording. Just take a moment and try to answer these questions yourself. Okay. All right. So the distribution, right? So we're showing a distribution, And so how many values are in this distribution? Well, if you think back, if you go back and think about the demo, what did we do? So for the gold, as we show from here for 900, we were taking for each trial that we ran, our sample size was 900. So every trial we took, a sample size of 900, and we did that, and we did that, and then we from that sample we computed our sample average, right? That gave us our mean. That was our one statistic, and we did that trial 10,000 times. And the distribution that we're looking at is the result of all 10,000 of those trials. The 900 in the graph refers to the sample size. So each trial, each one of those 10,000 trials, the gold bar we picked 900, and for the blue we picked 400. Okay, so for the first blank, right, it is 10,000 values, each of which is what? Well, we're computing on that sample. We're computing the statistic. Right? And so the answer is going to be D. That statistic is the average of flight delays. Okay, so for this example here, the gold histogram shows the 10,000 of our average flight delay, and you can see overlaying the two histograms one on top of the other, you can absolutely see what's happening. Right? Again, the average, the peak of the curve, is going to be our estimate of the sample, our estimate of the average flight delay from there. And you can see that in the gold case, what happens is that it's getting narrower and it's getting taller. It's getting taller from there. More of the samples are converging onto a more narrow range. Okay. Questions about that graph? Okay. All right, so now let's take a look. So this is everything that I just said in PowerPoint, in slide form for there. So you have the answer and the reference for that. Okay, so now we can now put this more formally, right? So I was trying to with the last demo, I was trying to give you some kind of just intuition here, and that the idea here is that the more sample size, the more that we sample, the narrower, but there's limits, and the limit actually comes from, as we saw, kind of bringing in this variance of the population itself. Okay, and so the distribution of all possible sample averages of a given size, that's called the distribution sample average. Okay, so that is all possible samples of the population. Okay, and that would be even a huger undertaking, right? Let's kind of put this in context. That would be even a huger kind of undertaking, right? Because it is all possible samples from there, right? In a practical sense, if you would never do this, okay, you would absolutely never do this, because it would be just easier to get the whole entire population, right? Because this is all possible permutations of different samples, and to do that, right, to get all possible sample averages, you would need the entire population anyway. So that is something you would never do in practice, but if you had that, right, if you had that distribution, you would have everything that you needed from there. And so we're not going to do that. We're not going to do that. But what we've done time and time again, we're going to approximate that by our empirical distribution, right? We're going to say we're not going to have all possible samples, but we're going to approximate it by the empirical. Okay. And by the central limit theorem, right, if our sample is large and random enough, the center is going to be the population average, right? We've been saying that all along, nothing from there. But now we can formally kind of put some understanding about the standard deviation of our empirical distribution. And so the standard deviation of our empirical, the thing that we're going to measure, is going to be the population standard deviation divided by the square root of the sample size. Okay. And so there's a couple of interesting things of this point. So notice in this equation, right? So this is going to give us the standard distribution of our empirical distribution, right? The one that we sampled from there. Notice that it has nothing to do with the size of the population. The size of the population is nowhere in this. It is all captured in the population standard deviation. Okay, and so what it shows us is that our standard deviation will go down when we increase our sample size, but there's a limit because it's going to be the square root of the sample size, right? So if we wanted to have the standard deviation, we would have to double. We would have to more than it's not linear. It's quad, right? So we'd have to do it by the square of the sample size from there, and we are limited by the actual standard deviation of the population. If the population is more varied, it's going to require a larger sample size to reduce the population. Let's take a look. Variability, yep. And let's take a look from here, okay? All right, so put this in context again, airline data. All right, it's gonna take a few moments to run. While it's running, let me know if there's any questions. Okay, and so this is the graph that we saw, and it's always good to know the code where our graphs came from here. And right, so this is just straight up application. There's no new code in demo here, but it's nice to kind of see that overlay from there. Okay. So I think I have time for this. I think, yeah, let's do this demo. Let's at least get started. Yeah, let's do this demo. And so what we're doing here is we're going to basically do a plot with, so we kind of on the previous diagram here, we just looked at two different sample sizes here, and so here we're going to run a bunch of them. Okay, and this takes like about 5 or so minutes to run. So I've pre-run it because I want you to kind of see this table here from here. Okay, and so what we've done here with our data, and because we have the full population, we have everything, and so we just did a bunch of these graphs, right? So we picked, the other place we picked 400 and 900, and here we've done it for a bunch of different sizes. Okay, and so what we've done is we've taken that equation, because we have the population, we have the ground truth, and so the blue is the standard deviation of our simulated sample means. Okay, so that's the standard deviation of our empirical distributions. Okay, and this is the theoretical. The gold is the theoretical. That is this equation. Right here. This is this equation here. because we have the ground truth, we have the population standard deviation, and we have our sample size. That's just the input that we provided. This is the calculated standard deviation. And then when we look at the two of them together, aha, they match, right? They are very, very close to one another. They are very, and remember, this is the blue line is random. It is random, and so it's not going to be perfect. And if we run this, another time, we'll get slightly different. But you can see that this holds for this whole duration of sample sizes from here. And as we can say, right, so on the y-axis, this is our standard deviation, and you can see as our sample size increases, the standard deviation goes down from there. Exactly to that formula. Okay. And so, all right. This is actually a perfect stopping place from there. We got through pretty much.
Okay, let me share my screen. So we're gonna resume from topic 22. Okay, so that's the topic where we were almost done, I think, last Thursday with Jason about distribution of sample average. Okay, and if we come back here, just I guess quickly going over the stuff that we talked about last Thursday, roughly. Okay, so we are focusing on the distribution of the sample average. Okay, and then remember, it is a distribution because every time you take a different sample, you might get a different sample average. Okay, and then if you do it for a large number of times, as we know, you might get each time different, right? That's what we mean by it as an estimate. So, so there is a natural distribution, okay, for the sample average. And so this set of slides talks about why there could be, okay, so this is the example, like, this is, say, like the population, right? Like every time you have a different sample, you take the mean and you realize that the sample mean has a distribution. And then in particular, we talked about based on central limit theorem, right? This is going to be a normal distribution, okay, centered at the population mean. Okay, so that's why we focus on a lot of times the inference about the average, because we do have some really good property or useful properties, like it follows a normal distribution that we can do hypothesis testing or confidence interval for. Okay, so then of course, then we talked about the variability of the sample average, okay, because every time you get it slightly different. And then, so naturally there will be some variability, okay, but more importantly, I guess, from last Thursday is that we realized the sample size is going to play a role. Okay, the sample size is going to play a role when we're thinking about the variability of the sampling of the distribution of the sample average. Okay, so this example, if you remember, is in the demo that we did for two different sample sizes. Okay, 400 and 900. Okay, for each we did, I guess, 10,000 simulations, right? So here we're doing the overlaying histogram of two different colors. And then the 400, which has a slightly wider spread, okay, that is the sampling distribution, okay, or I should say the empirical distribution of the sample average when the sample size is 400. And then the gold color, which is a little bit more concentrated with a smaller spread, that's the case for the sample size of 900. Okay, so what we have noticed, I guess, from the biggest takeaway from this is that both of first of all, the number of data points in each of the histogram is 10,000, okay, because each one is representing a sampled statistic, okay? And then what we notice also is that for both distributions, they're roughly bell-shaped, okay? And more importantly, for this comparison, we know that the larger the sample size, the narrower the bell, okay? Meaning that the larger the sample size, the variability of the sample mean shrinks. Okay, intuitively, hopefully makes sense, because every time if I take a larger sample, it's more like it probably will hopefully be more like related to the population mean, like closer to it, because I have a larger sample to estimate. So this actually can be manifested, as you can see, if we compare different sizes. And I guess one other thing is that both of them are centered at the mean of the population as well. Okay, so this is examples and then demonstrations of how the central limit theorem is working in practice, okay? And then for us, it's important to note about how the sample size plays a role into the variability. And then, of course, we talked about, I guess that was how we ended last Thursday-ish. Oops, here is the standard deviation, right, of the the sample average that we can actually compute it from a normal distribution as the population standard deviation, if you have it, okay, divided by the square root of the sample size. Okay, so that's what we covered, I think, by last Thursday. And then, of course, in practice, I mean, mathematically, if you want to compute it, then you need to know the population standard deviation, okay, and then also the sample size. And then if you look at this mathematically, suppose the population standard deviation is fixed for a particular population, right? And then as a sample size of 400 versus a sample size of 900, we can see that the square root of that is 20 versus 30, right? And then what this shows is that the larger the sample size, like the 900 case, which gives us a square root of 30, square root value of 30 here, the larger the sample size, the smaller the standard deviation, okay? And that's exactly what we're seeing over here, okay? So these are very widely used results, okay? And then in the demo, I think you see even more different sizes and just as a comparison, but clearly you see that trend going on, okay? So that's a recap, okay? And then for this, to wrap up this topic, we have a series of discussion questions, okay? So there are actually 3 of them, I would say. So let me talk through them quickly, and then I put you in the breakout room. So I will highly recommend you to go to the course website to look at the 3 different questions, especially the last one has a few figures. But let's talk about them quickly and then put you in the breakout room so you can discuss among yourselves, okay? So the first part of the discussion question is, they give you, okay, a population size, okay, 500,000 households, okay, they give you the annual incomes of these households, the average and the standard deviation, okay, they ask you the distribution of the incomes is what, okay, ABC, okay, pick one and explain, okay. Then we move on to talk about from this 500,000 households as the population, right, we're taking a random sample for 900, okay. And then we're asking you, fill in the blanks and explain. There is about 68% chance that the average annual income of the sample households is in particular range, with 2 blanks down there to ask you to fill it out. So you might need to take out pen and a paper and then just do the math really quickly. And the last one is we give you, so this is not related to the previous 2, okay? Population has an average have a mean 70 and standard deviation 10. Okay, they ask you that A, B, C, the 3 choices, one of them is the empirical distribution of the averages of 10,000 random samples of a size 100. Okay, so which one? All of them have exactly the same shape pretty much. Okay, so think about what matters here and then how you're gonna do the choosing between the 3. Okay, so remember all of the stuff that we recapped just now about like sample sizes and then the normal distribution, how to do this kind of calculation. And then of course, this is just a quick hint. This reminds us the 68, 70, 68, 95, and 99.7 rule, if you remember, okay, about the normal distribution. So that will be useful as well, okay? All right, so I will stop sharing and I will stop recording. Okay, yeah, so we have 3 questions in total. And yeah, since I guess, yeah, pretty much all of them, I guess, can be answered either verbally if you want to speak up or type in the chat. So for the first one, the distribution of the incomes should be A or B or C. And feel free to type in the chat or speak up, just unmute yourself and then share what you think. We really appreciate it. Okay, so I got a C in the chat, okay? Everybody agrees, disagree? Comments? Okay, yeah, Samantha, do you mind sharing why you think C is the option?
Sure, because it never really specified that the sample was like done randomly, or it was, so I just assumed like we couldn't assume a normal distribution.
Yeah, well, good point. Yeah, I will just also add that I think at this stage of the question, it's not about the sample yet. Okay, let me close my windows a little bit loud. Because here the city has 500,000 households, and then this 65,000 as well as the 45,000, I think they're the population parameter. Okay, you're given because they're talking about the entire population. of all of the households in the city. Okay, so then for us, we only know its average and its standard deviation, but it doesn't tell us anything about the distribution of the incomes here. This is the population distribution, so I think it's it will be C. Okay, so this is at the stage of only talking about the population. Then if you remember what we had talked about before, whether it's the population or the sample, like the distribution of that could be anything, right? Like could be, I don't know, like can be uniform, all equally likely, or like a normal, or maybe, I don't know how, like it could be anything. And a lot of times for income, for example, it will be a really highly skewed distribution, okay? Like with a really long right tail, because very few people make a lot, okay? But then the majority is probably, I don't know where, but it's going to be maybe around the mean or close to the mean. So most likely, okay, the distribution of the incomes will be something pretty skewed and not close to normal, okay? But we don't know, like we don't even need to know that, I guess, at this point for the ABC, to choose between ABC. But as we know, what we care about is once we start to look at the sample mean, right? And then the central limit theorem guarantees that is the average, the sample means themselves going to follow a normal distribution center at the population mean, right? With the standard deviation of that formula that we showed earlier. So that's what matters more for us. Okay, so thank you, Samantha. And I just try to also add a little bit other discussion over here. So it should be C. And for us, this is only about the population. The population distribution can be anything. Okay. All right, now we come down to the actual sampling part, okay? We're told that the sample size is 900, okay? Then the question is, there's about a 68 chance that the average annual income of the sampled households, okay? So be really careful about what they're saying, okay? They're talking about the average income, right, of the sampled households. So put into our usual wording, I guess, is the average, sample average, okay? That whole thing is like what we've been talking about, sample average, okay? So we know that it's gonna follow a normal distribution, right, roughly, okay? With mean at the population mean and standard deviation with that formula. So what do you think about these two blanks? Anyone is willing to give it a try? Either in the chat or speak up.
We said 65,000 plus or minus 45,000.
Okay, so I'm just typing in the chat. So Eli's team, I guess, is answer is this pair, right? Am I right?
Yeah.
Okay, thanks. Yeah. Everybody agrees? Or disagrees? What is that? Is that yes? Sorry, Sandy. Or is that half of an emoji? Couldn't even tell. I guess that's a yes. Okay. Anybody else? Everybody agrees? No disagreement? Okay, so Eli, do you mind like to maybe talk us through of why you chose those two numbers?
Yeah, like with the what is it, the empirical rule? It's 68% is plus or minus 1 standard deviation from the average. So since the average is 65,000 and the standard deviation is 45,000, it's just plus or minus 45,000 from the average.
Yeah, so indeed, yeah, that 68%, like we're reviewing earlier, refers to, I think, the 68, 95, and 99.7 percent rule, right? That we know that for normal distribution, within one standard deviation, you have 68% of the probability. Okay, within 2 and within 3 is 95 and 99.7. Okay, so if we focus the question, okay, so we know that they're talking about the sample average. Okay. And the mean, we know that the population mean is 65,000. So I agree that given central limit theorem, so let me come back a few slides ago, okay? By the central limit theorem, we know that the sample average, okay, gonna have the center at the population average. So I agree. For the first blank, I think is 65,000, okay? Because that's what the population average is, okay? And I also I'd agree with Eli's logic of, okay, 68 refers to 1 standard deviation. So whatever should comes in here is about 1 standard deviation. Okay, you don't need to multiply it by 2 or anything. I guess my only comment here is that if we come back again about the standard deviation, okay, so the standard deviation here, notice because we're talking about the sample average. Okay, that's what the question is, right? The chance that the sample average going to be in the particular range. So the standard deviation that we're looking for should be the standard deviation of the sample average, but not the standard deviation of the population. Okay, so what is given to us? So let's slow down. Okay, the question is saying that there are 500,000 households. We have the standard deviation, we have the population mean of 65,000 and population standard deviation, okay, of 45,000, okay? And then the question is asking us, okay, about the distribution or certain feature, right, of the sample mean. So we need to work on everything on the sample mean, okay, where the mean is the population mean, okay? And the standard deviation actually needs to be the population standard deviation divided by the sample size, square root of the sample size. Okay, so if we do the math quickly here, I guess it's 45,000 as the population standard deviation, right? And then we have 900, right? Square root of that is 30. So you divide 45,000 by 30, which I guess is 1,500, right? 1,500-ish. Okay, so does that make sense? Or because everybody, I guess, agreed with Eli's answer. So I wanted to make sure that, do you have any follow-up questions about this? Anyone? Or it doesn't make sense, or it doesn't make sense, or you think the wording is a little bit tricky, so you didn't get to the point earlier? Eli, does it make sense, the answer that I provided just now?
Yeah.
Okay. Yeah, no, thank you. I didn't mean to put you on the spot. I appreciate you offering the answer. And yeah, so I guess in this case, just be a little bit careful. And I guess another way to double check our work is if we come back to the previous question, right? If you chose C, right? Then we know that, well, when you chose C, which I believe most of you did, then we are acknowledging that we don't really know about the distribution, right, of the population, okay? So again, this is the population mean and this is the population standard deviation. So while you probably will never use this two together to do any kind of normal calculation, okay, because they do not follow, like the population distribution itself does not follow a normal distribution. So you wouldn't use themselves directly, right? But then for us, it's indirect because of the fact that by central limit theorem, we know that the sample average follows a normal distribution with the mean at the population average and standard deviation is the population standard deviation divided by the square root of sample size. So that's why you're gonna have 65,000 here, but then here going to be 45,000 divided by square root of 900. Okay, all right, what about the last one? This is not related to that setup. Okay, you have an average of 70 and standard deviation 10. Notice that they told you they are the population parameters, okay? So this is again, that we know about the population, the mean and the standard deviation. And then we're doing this histogram of empirical distribution of the means, again, okay, averages, of 10,000 random samples of size 100, okay? Which one do you think is referring to the histogram of what we're doing here and why?
Would it be B?
Okay, so we got one from Samantha again. Thank you. Okay, so Samantha says it's B. Okay. Anyone else? Okay, we got, okay. Somebody private messaged me. Okay, maybe it was meant to for everyone, but I got an A. Okay, so we got two different answers now. Okay, we got another A. Okay. Okay. So yeah, I'm just going to invite Sandy, if you don't mind sharing what you did, because I talked to earlier, I invited Samantha earlier, and also the other A was private message.
Because it's the empirical distribution of the averages, and we got a large sample size, so it should be normally distributed. And so the Chebyshev inequality says like within the three distribution, but three standard deviation, we should be able to cover the entire sample. And one standard deviation is 10, so like, 3 standard deviation, we should be up to 100 and down to 40. And A is the histogram that describe what I said.
Thank you, Sandy. Okay. Yeah, thank you. Sorry. Yeah. Samantha, do you want to add anything about why you chose B?
Well, originally my group did pick A, but just based on like you explaining the answer to the last one, I was just wondering because you said the populate, since they give you the population standard deviation, I was like, oh, do we have to use the formula again? So the square root of 100 is 10 and the population standard deviation is 10. So 10 divided by 10 would be 1. And so even though I originally picked A, at the last second, I was just wondering if it could be B.
Yeah, indeed. I think in this case, it should be B, just exactly the reason that Samantha shared. Okay, so I guess this is related to the previous question a little bit, right? So like here, we're talking about a sample of a 900. So we use the formula of population standard deviation divided by the square root, okay, of the sample size to get the standard deviation of the sample. So for us here, again, we need to read it carefully. Okay, the first sentence told us that the mean is 70. Okay, standard deviation of the population is 10. So both 70 and 10, they're the population parameter. Okay, and just like Samantha pointed out, that it's standard deviation of the population is 10, but then we're doing sample size of 100, right? So we need to do 10 divided by square root of 10, which is 1 in this case, to get the sample standard deviation, okay, or the standard deviation of the sample mean. Sorry, let me put that in that way. The standard deviation of the sample mean, and then just like what Sandy was saying earlier, by the Chebyshev's rule, a majority, right, close to I guess in this case normal in particular. So like almost like 100% of all of the data points should be within 3 standard deviations away from the mean. That's why when you have a sample mean, the mean of the sample means at 70, and then the standard deviation of that at 1. So you should range from 67 to 73. Okay. Yeah. Does it make sense now, Sandy?
Yes.
Yeah. Okay. Yeah. Thank you both. Again, didn't mean to put anybody on the spot, and I hope you don't feel bad of like say sharing wrong answers. And we really appreciate like having this kind of discussion. So I guess those two are definitely related. Okay. I guess it's easy to make the mistake. Okay. What standard deviation we're really using. Okay. So I guess for us, just to recap one more time. Okay. So when we're working with the population, okay, it doesn't have to like, we don't even know what kind of distribution the population should be. Okay. It could be anything depending on the nature of the variable. Okay. But if you're given the population mean and the population standard deviation, then if you are working on a distribution of the sample average itself, okay, not the sample or not the population or not the observations themselves, okay, we are talking about the sample average, the distribution of that, then we know by central limit theorem, it's going to be roughly a normal distribution at the mean of the population mean and the standard deviation of the population standard deviation divided by the square root of the sample size. Okay, so given that, we worked out the second question, okay, because we have the mean of the population, but then this standard deviation is to be divided by the square root of sample size. And similarly here, we'll have to do that as well. Okay. And one last comment about A, I guess another way. So if like, let me ask, I guess the follow-up question, what A could be? Okay. Like just say like, if A is given to you, like what could A be given this setup? Like we know the answer to this particular question is B, right? And C is, I don't know, just I randomly put it there. But what could A be given what Sandy shared earlier? Any thoughts? It is not, I guess, the distribution. It's not the empirical distribution of the averages, okay, given this question, but I guess it could be a particular population, okay, of 10,000 observations, okay, and if you happen to have a population that is normal, then A could be the distribution of the population itself, okay. But just like what we were saying earlier, the population could be any kind of shape, right? Like it's not necessarily a normal. It could be any other distribution. Like I said, for income, it could be a really highly skewed, right skew distribution with a long tail to the right. Yeah. So this, like I said, could be like a very special population distribution that happens to be normal, okay? And then if we follow what Sandy said earlier, then A could be a distribution like that because we know that the mean is 70, right? And the standard deviation, right, of the population is 10, okay? So then by that rule, we know Chebyshev's rule, we know that, well, it should be between 40 and 100, okay? Like the range, because it's 3 standard deviations above and then 3 standard deviations below, okay? But regardless, I guess for this case, because the question is asking about the distribution of the sample averages, okay? So we need to, once again, be reminded about the standard deviation of the sample mean. It is the standard deviation from the population divided by the square root of the sample size. So that's why you're gonna have the answer B. Okay. Okay, makes sense, everyone? Hopefully. Okay, yeah, so take the time to revisit, I think. It's good, I guess, you get to talk with breakout room members to discuss what you think. And I guess not everybody got it right in the first place, right? So it might be good to revisit. And I will also say that because in our course, a lot of times we rely on simulation, right? And then whatever shows up in the graph, as long as you have done everything correctly, then you usually always use that graph or any kind of probability calculation you can use in Python to answer any kind of question. But I guess this kind of discussion questions that we talked about can also always be, well, I guess a good knowledge check, right? Just to make sure that we do understand what we mean by central limit theorem, right? It's about the sample average, it's not about the population observations. But at the same time, it could also be really handy, I think, to double check that your work in Python is correct, okay? It's not easy to spot, right? Like say, if we come back here really quick, sorry to drag on this a little bit more. If we come back here really quick, let's just say like, well, like for some reason you come up with A, okay, in your simulation when what you're trying to do is actually only the sample mean distribution, okay? So if you come up with A, like if you look at the range, right, of X, that is probably telling you that something was not entirely correct in your simulation, okay? Because we know if you're working on the sample, you know, like the distribution of the sample mean, then it should follow the normal distribution, center the population mean with standard deviation SD of the population divided by square root of the sample size. Okay, so if you get something like B, great. If you get something as A, that might make you rethink and revisit how you were coding, and maybe something was off a little bit. Okay, so nevertheless, I think make sure that you revisit this as needed, and then always reach out whenever you have questions.